Hi everybody, it's Mr. Duffy. Welcome to our chemistry lesson for today. In previous lessons, we've talked about the development of the periodic table and some of the groups that are on the periodic table. But today we're going to be using the periodic table as a tool to kind of show us some different trends in the elements as it's arranged in our modern periodic table. Let's go ahead and get started. So one of the first trends that we've got on the periodic table is our melting points of the elements. Now, this trend isn't really 100% perfect, but in general, on the left side of the periodic table, a lot of these metals, they kind of decrease in their melting points. On the right side of the periodic table, we have a lot of these elements, these noble gases especially, they're increasing their melting points. So again, different trends, but what we can kind of see in the periodic table in general is that basically in the middle of the periodic table, in these transition elements, that's where we have the highest melting points. Tungsten, other than carbon, which carbon's a kind of a unique element in itself, comes in different forms, but in a diamond form, carbon has the highest melting point of any element. But tungsten is the second, and again, you can kind of see that the rest of them around them are also high melting points. Tungsten is used in old style light bulbs, not the nice new LED light bulbs, but incandescent light bulbs use tungsten as their element of choice to produce the light because, again, the extremely high melting point for that metal. Okay, so tungsten's our highest melting point metal, other than, again, carbon, our highest melting point element. Another periodic trend we can kind of see is densities. Density is very similar to melting point in a way. They're not the exact same element, but we kind of see in this general, in the transition metals, the middle portion of the periodic table, we see the highest density elements. Osmium, iridium, platinum, gold, those are extremely high density metals. As we move away from that area in the middle, we get lower and lower densities. So the higher densities are in the middle. It looks like, again, let's see, osmium and iridium have the highest. I think they're slightly different. Osmium is just, 300ths higher in grams per cubic centimeter, so in density. So very high densities. Osmium is our highest density element. Now, those are, again, general terms, but there are some other trends that we can kind of see that relate more to how the elements kind of are going to interact, per se. One of these trends is going to be definitely new to you. We've talked about density and melting point in the past, but electronegativity is something we've never talked about. Electronegativity is a concept invented by a man named Linus Pauling, and there's a picture of him. And he invented this scale, and it basically represents the ability of an atom in a molecule to attract shared electrons to itself. Came up with this scale called the electronegativity scale, and he assigned an electronegativity to each element, each atom on the periodic table. Okay. Now, the elements on the bottom left have the lowest electronegativities. These elements are below 1 on the scale. Again, this is just an arbitrary scale. It goes from 0 to 4. And so, again, the units per se, there are no units for it. It's just a numerical value. It represents the ability to attract electrons. So again, these elements in the bottom left are really not good at attracting electrons. Francium, again, 0.7, lowest one. And then we have a lot of the lanthanides, actinides here, between 1 and 1.5. We're moving across the periodic table. We're increasing our electronegativities as we're moving to the right. These fall between 1.5 and 2. And then we get to 2 to 2.5, a couple more elements there. We get some of those back in the transition metals. They had slightly higher ones, higher electronegativities. Then we're moving to 2.5 to 3. Just a few more elements getting added here. These are some of our non-metals. And then finally, from 3 to 4, we get the last group of elements that have the highest electronegativities. Nitrogen, oxygen, fluorine, chlorine, bromine, iodine. Those, again, are very, very high electronegativities, with fluorine being the highest. Now, you might say, Mr. Duffy, well, the noble gases are not even listed on here. What are their electronegativities? Well, they are not given electronegativity values because they do not really attract electrons. They are stable by themselves, and so they don't really have the ability to attract electrons, and so their value is 0. So excluding the noble gases, as we move to the right on the periodic table, the top right, that is where our electronegativities increase. Now, you might be saying, Mr. Duffy, how am I going to be able to remember that, these electronegativity values? Well, you don't have to. They are on your periodic table that I passed out to you in class. Oh, upside down though. And they're on the back here. It's a slightly different color scale than what I have on the slides, but again, it is there for you with the values. And on your periodic table, I go to 2 decimal places versus this slide, I went to just 1 decimal place. So you can kind of get a little bit more accurate value for the electronegativities. On the back of your periodic table, you do not have to memorize it. The next periodic trend that we've got is atomic radius. Atomic radius is basically how big the atom is. Again, radius, the atoms are a sphere, so in 3 dimensions. So their radius is a measure of, how big they are. We could say diameter as well, but again, same thing. Now, from this diagram on atomic radii, we can kind of see the main group elements. We see group 1 and group 2 here on the left, and then groups 13 through 18 on the right, 13 through 17 on the right. I didn't include the noble gases. We can kind of make some assumptions here or some predictions here as to what's happening with the atomic radii. Basically, as we kind of see, as we're moving down the periodic table, in every case, in every group, the atoms are getting bigger. And as we're moving from the left side of the periodic table across the period to the right side of the periodic table, the atoms are getting smaller. And so we want to, again, we can see that as a periodic trend, but I want to be able to try and explain why that is the case. So let's take a look, again, the exact same thing, but this is, again, just a few more elements, but it shows the exact same thing. As we are going, again, from atomic number along the x-axis and size along the y, we can kind of again see that, as we're going across the period, they are decreasing in size, and as we're going across a group, down a group, they are getting larger. It's a little bit harder to follow on the line graph, but this, again, graph does show more elements, so you can kind of, again, see what's going on, but it's showing you the exact same thing as the diagram I showed you in the last slide. So let's talk about the easier one, which is why are the atoms increasing down a group on the periodic table? Well, basically, as you're moving down a group, you're adding another energy level. Each energy level is further away from the nucleus, and so that makes the atom bigger. Pretty simple stuff. So here I have lithium, sodium, potassium. They are in group 1, the alkali metals, and lithium is the smallest at the top, and potassium is the biggest here on the bottom. Again, there are more elements below potassium, but again, these 3, potassium is the biggest. Okay. Now, with that being the case, why? Here is a Bohr model without the electrons, just the energy levels of lithium. You can see that it has 2 energy levels. Sodium adds a 3rd, so that makes it bigger. And potassium adds a 4th energy level. So you can kind of see again that as we move down a group, that is exactly why the atoms are getting larger. It's because you're adding these energy levels. Now, going across the period is a little bit more tricky. So, and to explain this, I need to again remind you why, what's going on with the size here, and it's all based on electrical attractions. Now, reminding you that basically opposites attract, positive and negative charges attract, and like charges like to repel. Now, the like charges, the positives, those are in the nucleus. They're being held together by the strong nuclear force, so that kind of holds them together. But electrons around the outside, again, they are going to repel each other as much as they possibly can. But again, it's all related to this balance between attractions between the nucleus, the positive charges in the nucleus and the electrons, and again, those repulsions between the electrons away from themselves. So the first thing we have to talk about when we're talking about going across the period and relating to the size is what's called the shielding effect. We have our nucleus, and around the nucleus go those different energy levels. Now, What really determines the size of an atom is the last level. We call them the valence electrons. They're the ones on the outside of the nucleus, the furthest away from the nucleus. But what happens with when we're talking about the size of the atom is the fact that these inner electrons, these core electrons, shield the nucleus from the outer electrons. They're kind of basically more attracted to the nucleus because they're closer, and they're keeping the charge away from those valence electrons, which are further away. Now, that really determines the size of the atom. How much shield there is determines how far away those valence electrons are going to be. The inner electrons block the attractive force from the nucleus from those valence electrons. Here's another diagram of this, showing you the shielding effect and basically a new concept which we can use to calculate the effective nuclear charge, basically how much pull those outer electrons get from the nucleus. Okay, so we have attractions and repulsions in an atom. Like I said, the attractions come between the electrons and the nucleus of the electrons and the nucleus of the atom, which have the protons. Okay, this is basically diagram of magnesium. The energy levels of magnesium. It has two valence electrons. So again, I just included the valence electrons here. The core electron, I'm just going to represent again with just one electron in the core, but there are more electrons in the core electrons. So two valence electrons and then some core electrons providing a shield from the inside. Now, those valence electrons, again, are attracted to the nucleus, but so are the core electrons. Again, they have a stronger attraction because they're closer to the nucleus. But all the electrons also repel away from each other. So the core electrons are repelling, they're pushing away those valence electrons. The electrons are, again, all still attracted to the nucleus, but they're also repelling each other at the same time. The valence electrons are also repelling each other. So basically, again, it's a balance between the attractions and the repulsions when we're talking about the size. This determines the size of the atom, how attracted to the nucleus there are. And again, you can imagine if there are more electrons on the inside, more core electrons, then that's going to create more of a shielding effect from those valence electrons who are going to be further away. And that, again, in turn, would make the atoms, again, bigger. Now, let's see that in a diagram. Let's look at another simulation of this. Decreasing atomic size across the period. This is period number 2. I've got lithium, beryllium, and boron here for you. Again, second group, lithium has 3 protons, 3 electrons. Beryllium has 4 and 4. Boron has 5 and 5. Okay, now, it's a balancing act, like I said, between the attractions to the nucleus and the repulsions between the electrons. So the attraction between the nucleus and the valence electrons increases as we move across the period. But the atomic size then decreases because the attraction is basically increasing as we kind of move along. So as the nucleus gets more and more positive charge there, we're getting a greater attraction to the nucleus from those valence electrons. And so again, a greater attraction means a smaller atom. So as we move from left to right, again, the size decreases because of that. But we have another way we can represent that. Again, we're increasing the nuclear charge, but we have another way we can represent this effect, is we call effective nuclear charge. We can basically take our number of protons minus our core electrons to give us a numerical value for how attracted the valence electrons are going to be to that nucleus. Now, each valence is then pulled by that full effective nuclear charge. The larger the effective nuclear charge, the more attracted it's going to be, and the smaller the atom's going to be. So let's put this to some numbers. I'm going to take this away. Lithium's here. We have 3 protons in the nucleus of lithium. We have 2 core electrons inside. Again, the core electrons inside, and we have 1 valence electron on the outside. So again, this is the Bohr model for lithium. Now, the effective nuclear charge here is 1 because I have 3 protons minus 2 core electrons, and that gives me an effective nuclear charge of 1. Not much pull from the nucleus on that 1 electron. Okay, so again, not much. It makes for a larger atom. Beryllium, on the other hand, adds 1 more proton to the nucleus. So we now have 4 protons in the nucleus, and it has 4 electrons, still though 2 core electrons. 2 core electrons. If we do the effective nuclear charge, the number of protons minus your core electrons, it gives an effective nuclear charge of 2. 4 minus 2 is 2. And so again, this is a stronger pull from the nucleus on each of those remaining 2 valence electrons. And so that actually shrinks the atom a little bit. It's a little bit stronger attraction from the nucleus, and the atom gets smaller. Boron just continues this exact same thing. It has 5 protons in the nucleus, 5 electrons as well, but only 2 core electrons still. 2 core electrons, 3 valence electrons. If I figure out the effective nuclear charge, 5 minus 2 is 3, effective nuclear charge of 3. That means, again, those valence electrons are going to get a little bit more pull from the nucleus, and that, again, will make the atom smaller. So more pull from the nucleus, a larger effective nuclear charge, you're going to get more, a smaller atom, more pull on those valence electrons. To summarize, as we move down a group on the periodic table, the atoms get bigger because we are adding a new energy level. As we move from the left side to the right side of the periodic table, our atoms are getting smaller because a greater pull from the nucleus and, again, a larger effective nuclear charge. Okay, so that is why we see these trends in the atoms as we, again, look at it on the periodic table. Okay. Last thing we have to talk about is ionic size. Ions. Ions are when atoms gain or lose electrons. Again, we do this to become more stable. We talked about this in the last unit. But ionic size, again, you can imagine gaining or losing electrons is going to change the size of the ion. And so there's 2 ways you can do it. Again, cations are formed by losing electrons. You can imagine if you lose an electron, the atoms are going to be smaller than the original atom they came from. If you lose an electron, it goes away, again, the atom's going to shrink. Metals normally do this. Metals normally lose their electrons and form cations, and again, they do this to form a noble gas electron configuration, which, again, we'll get to at some point in time. Here's a good example of lithium again. Lithium will like to lose 1 electron. It likes to lose that outermost valence electron. And when it does that, it gets smaller. So here's again, example of that. Energy comes in, kicks off that electron, and again, it removes that energy level. Lithium becomes much, much smaller by losing that 1 electron, and it becomes a positive ion. So there's a comparison. The lithium atom has a size of 152 angstroms, and the lithium ion with a positive 1 charge is 60 angstroms. So much, much smaller by losing that 1 electron. Now, obviously, the opposite. This is a diagram of this in general. This is the atomic radii of all elements here. And if they lose an electron, you can see they got, again, much, much smaller here in this case when they lose their electrons or okay. The other thing would be, well, what if you gain an electron? Well, anions are what happens when you gain an electron. Anions are bigger than the atom that they came from because if you're adding electron into the atom, you can imagine you're increasing in your size. Nonmetals normally form anions. Nonmetals, they do this, again, to form a noble gas electron configuration. So, valence electrons, again, are repelled by each other. And so by adding another electron basically without changing the effective nuclear charge, you're going to increase the repulsions in the atom, in the ion. And so here's fluorine, for example. Fluorine has 9 protons, 9 electrons. And if we add an electron, which fluorine normally does like to do, it normally likes to add 1 more electron, we get 10 electrons. Well, those 10 electrons, again, there's more than there were before, they repel each other. And that repulsion is going to cause them to increase the size of the ion. Here's another diagram of this. There's fluorine, 9 protons in the nucleus, 2 inner core electrons, and 7 outer valence electrons. This is the normal atom by itself. Let's say I want to add an electron in here. the valence electrons by themselves are repelling each other, but if I add another electron in, you can see that, they're going to have to push to have that same repulsion away from those electrons. They're going to have to push away from each other more, and when they do that, that increases the size. That increases the size of the ion, and the ion gets, again, bigger there. So that would be our fluorine ion.